RC series AC circuit. This is an AC circuit which contains a resistor and a capacitor connected in series, as we can see here. You see, the combined opposition to the flow of alternating current here by the resistor and capacitor is known as impedance. The impedance is actually giving us R square plus XC square all into square root. Hence, our voltage supply now is going to be current in the circuit times the impedance. Again, this same voltage supply can be obtained by saying square of the voltage in the resistor plus square of the voltage in the capacitor all into square roots. Likewise, you see, the phase angle phi, phase angle, can be obtained by saying doing tan inverse of the XC over R, or tan inverse of VC over VR, voltage in the capacitor divided by voltage in the resistor. You see here, our phase angle is usually negative actually. And that's because, you see, this is between a capacitor and a resistor. And remember, in a resistor, the phase angle is 0 degree. But in a capacitor, the voltage lags the current by an angle of minus 90. By the time you combine these two components in an AC circuit, you realize that your phase angle will lie between 0 and 90. So it will always be negative. It won't be 90 actually, and wouldn't be 0, but lies between 0 and 90. So the phase angle in an RC or in a RC AC circuit is usually negative. And so it means that the voltage will still be lagging the current, but by an angle that is greater than minus 90 but less than 0 degree. Example 6. A resistor of 25 ohm is connected in series with a capacitor of 45 microfarad. Calculate A, the impedance. B, the current taken from a 240 volt 50 S supply. Find also the phase angle between the supply voltage and current. Let's solve this now. First of all, what are we given here? We are given our resistance, which is 25 ohms, and we are given our capacitance of the capacitor, and that's 45 microfarad, and that's 45 times 10 raised to the power minus 6 farad. We are given our voltage supply to be 240 volts and the frequency to be 50 Hz. Okay? Now, firstly, we have to get impedance. To get our impedance, we need our XC, capacitive reactance. And so I will say XC is equal to 1 over 2 pi FC. And that will be 1 over 2 pi times the frequency 50 times 45 times 10 raised to the power minus 6. And this will give us 70.74 ohms. So this is our capacitive reactance. Now the next thing we need to do here now is to calculate our impedance straight up. And so our impedance is given by the relation R square plus XC square all into square roots. And so that would be 25 square plus 70.74 square, all into square root. If we evaluate this, we are going to have 75.03 ohms. So we have our impedance now. The next question is, we should calculate our current. And so we know that the voltage supply is equal to IZ. We already have our Z and we have our V. So our I simply be V over Z. The V being 240 volt, that's supply voltage. And then our impedance is 75.03. So if we divide this, we are going to have 3.20 ampere. Now, lastly, we have to get the phase angle. The phase angle phi is simply tan inverse of XC over R. And that's tan inverse of the XC, capacitive reactance, is 70.74 divided by the resistance, which is 25. So the phase angle will simply be 70.54 degree. So that's all for this question. Example 7. A capacitor is connected in series with a 40 ohm resistor across a supply of frequency 60 Hz. A current of 3 ampere flows and the circuit impedance is 50 ohms. Calculate A, the capacitance of the capacitor, B, the supply voltage, and the PD across the capacitor and resistor. So firstly, let's bring out what we are given here. Here, we are given that the resistance is 40 ohm and then the frequency is 60 Hz. And then again, the current is 3 ampere and then the impedance is 50 ohm. Okay? So firstly, we want to get the capacitance of the capacitor. To get that now, capacitance. So we are looking for C first. To get that, we need to get our XC. We know that Z square is equal to R square plus XC square, all into square root. So remove the square here. So we can say Z square is equal to R square plus XC square. We have the Z to be 50. So 50 square is equal to 40 square plus XC. So bring this one here, we get 25 minus, this is 16. Bring it here, minus 16 is equal to XC square. So our XC square is equal to 900. So XC will be equal to square root of 900, which is equal to 30 ohms. So we've gotten our XC now, which is capacitive reactance. We cannot get our C, capacitance. We know that XC is equal to 1 over 2 pi FC. So C, making C solve formula, C will be equal to 1 over 2 pi FXC. And that is 1 over 2 pi times 60 times our XC, which is 30. So if we do this, we are going to have 8.84 times 10 raised by minus 5 farad. So we've done the first one. The next one now is the B, the supply voltage, which is V is equal to IZ. And our current in this question is 3 and our impedance is 50. So that's 150 volts. The next one now, C, the V across the capacitor. And that is IXC. The current is 3, but our XC is 30. And that will give us 90 ohms. And then the voltage across the resistor is IR. And that will be 3 times our R is 40. And that will be 120 ohms. So that's that for this question. RLC series AC circuits. This is an AC circuit which consists of a resistor, inductor, and a capacitor connected in series. And such a circuit is as shown as this. The combined operation of flow of current, as you all know, is still called impedance. And now, the impedance, we can have different relationship for the impedance depending on which is greater. If the inductive reactance is greater than the capacitive reactance, then the impedance will be given as R squared plus XL minus XC, all squared, all into square roots. And then the phase angle will be tan inverse of XL minus XC over R. But if XC is greater than XL, then impedance will be given as R squared plus XC minus XL squared, all into square roots. And the phase angle will be equal to tan inverse of XC minus XL over R. Now, it's important to note here that if XL, note, let me put this as a note, if XL is greater than XC, then the phase angle is positive, and if XC is greater than XL, then the phase angle is negative. It's actually easy to ascertain this. Let's come here now. If our XL is greater than XC, by the time we subtract, the remaining value here will be the value of XL, with which it is greater than the XC. And so it should now look like XL and R, because SL was greater than XC. And we know that the phase angle should be positive in an SL-R series AC circuit. Again, if our XC is greater than XL, by the time you subtract, you see, if I say, let me assume that SC is 100 and SL is 70, by the time you subtract, you get 30. That 30 you have is the value for XC, the amount by which SC is greater than XL. So it now look like an XC-R series AC circuit, and we know the phase angle will be negative. And that's because SC is greater than XL. So that's what we put here as the note. Then our voltage supply is still IZ. It doesn't have, maybe it is XC or XL greater than anyone. It's just IZ. So we'll take an example under this now. So let's look at this example 8. A coil of resistance 5 ohm and inductance 120 millihenry in series with a 100 microfarad capacitor is connected to a 300 volt 50A supply. Calculate the current flowing and the phase angle between V and I. So let's solve this question now. Firstly, what are the things given in this question? We are given that our resistance is 5 ohms, and then the inductance L is 120 millihenry. That is 120 times 10 to the minus 3 henry. And we are given the capacitance is 100 times 10 to the power minus 6 farad. That is a microfarad. And then the voltage supply is just 300 volts, and the frequency is 50 Hz. Okay? So the first thing we want to do is to calculate the impedance. That's what we're supposed to use before we can get the current. Now, to calculate our impedance, we need to know our XL and XC. So our XL, which is 2 pi FL, will be equal to 2 pi times 50 times our L, 120 times 10 raised to the power minus 3. So this is what we have. If we do that, we're going to have 37.7 ohm for the inductive reactance. Now let's calculate capacitive reactance now. That's 1 over 2 pi FC. And that's 1 over 2 pi times 50 times 100 times 10 raised by minus 6. So this will give us 31.83 ohms. Okay, now the next thing to do is to calculate the impedance. So our impedance now, since XL is greater than XC, our impedance Z will be equal to R squared plus XL minus XC all squared, all into square root. Our R here is 5 squared plus 37.7 minus 31.83 squared, all into square roots. So if we evaluate this, we are going to have that our impedance is equal to 7.71 ohms. Now, the next one is the current flowing. That's the first thing we actually have to get. So our current flowing is that V is IZ. Voltage supply is I times impedance. So I will be V over Z. And then our voltage is 300 over 7.71, our impedance. So if we do this, we are going to have 38.91 ampere. Now, lastly, the phase angle. For the phase angle, phi, it is tan inverse of XL minus XC over R. So that will be tan inverse of the XL is equal to 37.7 minus XC 31.83 all over R 5. If we do this, we are going to have 49.58 ohms. Resonance in RLC series AC circuits. Resonance occurs in an RLC series AC circuit when XL is equal to XC. You see, at resonance, the impedance is minimum. And that's because, you see, the impedance is always greater than the value of your resistor or inductor or capacitor in the circuit. And that's because, you know, impedance is R squared plus, it's not just R, plus something else again, XL minus XC. So because something else is added to the resistor, the impedance is always higher than the value of the resistor on a norm. But now, since SL is same as XC, this value will give you 0. So nothing adds to the resistance. And you know there's a square root here. So you just have that Z is now equal to R squared and the square root. This square root cancels this square. So Z is R. So that brings down the value of our impedance. And it's not exactly equal to the resistance in the circuit. So have it in mind that at resonance, our Z is equal to R. And that Z value is actually the minimum value in that series RLC AC circuit. Again, the current is minimum. You know that current is V equal to IZ. Actually, these are current. Now, if the value here is minimum, that I is equal to V over Z, that's what I wanted to write. Now understand that if A is minimum, then the value here should be maximum. And that's because Z is taking a smaller value, which is the value of R. Then your I should be maximum. So that's about that. Now, let's obtain the resonance frequency. We know that at resonance now, at resonance, XL is equal to XC. Therefore, we know that XL is 2 pi FL, which is, I'll call it FR, because this frequency is the frequency at resonance. And that is equal to 1 over 2 pi FR also, but times C. You see, if we cross multiply this now, we are going to have 2 times 2, that's 4. Pi times pi, that is pi square. FR times FR give us FR square. And L times C will give us LC. And that is equal to 1. So we now have it now that the resonance frequency square is equal to 1 over 4 pi square LC. Now, if we make resonance your formula, resonance frequency your formula, we have that FR is the square root of 1 over 4 pi square LC. Square root of 1 is 1. Square root of 4 is 2. Square root of pi square is pi. Remaining LC. So this is the formula for the resonant frequency. Example 9. A coil having a resistance of 10 ohm. Okay. So we're giving the resistance 10 ohm and an inductance of 125 millihenry. L 125 times 10 raised by minus 3 Henry is connected in series with a 10 microfarad capacitor. 10 times 10 raised by minus 6 farad capacitor. Across a 120 volt supply, voltage supply is 120 volts. Okay? At what frequency does resonance occur? Find the current flowing at the resonance frequency. So very simple now. The first one, we have to get the resonance frequency. And that's 1 over 2 pi square root of LC. And that's 1 over 2 pi square root of the L 125 times 10 raised by minus 3 times C 10 times 10 raised by minus 6. So if we do this, we're going to have 58.12 Hertz. That's the resonant frequency. The next one is the current. So that's the B. To get this now, we know our current is V over Z, which is as V over our R at resonance. At resonance, the value of Z is same as value of R. And so if we do that, we're going to have our V, voltage given us 120, while the current in this question, I didn't bring out the value of the current. Okay, we have our R, sorry, to be 10. It's current you are looking for, don't mind me. So this will give us 12 ampere. So that's that.